Hello and welcome back. Right now I want to give a short excursion into the wonderful world of differential item functioning, something that we have been talking about quite a bit already without really using the name. And I will also try and make a point of why it is important that we care about diff as it is commonly known, and I will link it back with the various steps that we have discussed already with confirmatory fact analysis. First of all, why should we care? We should care because differential item functioning is very important for all sorts of evidence-based decisions that people are making. So if you select people into, for example, companies, so job selection, if you decide what kids go to what kind of school or whether you can get into university or not, then you need to worry about your tests and whether they work equally across different groups. If you need to make a decision about where to spend money, you need to have data. Again, you need to know whether your tests are working or not. And of course, as psychologists, we are often worried about how we should best diagnose and treat individuals with psychological or mental health issues. And so we rely a lot on tests, and we need to worry about whether those tests are actually measuring the right construct. So all of this basically means we need valid and scientifically grounded instruments. So instruments that we will see in a second that do not have differential item functioning, because if we don't have that, then we will very likely have a negative impact on certain groups within society. So what's the problem? First of all, tests may discriminate against specific groups, for example, different genders, different age groups, occupations. One issue that we're very much concerned about in this course is culture. There might be tremendous societal implications if you negatively impact certain groups. It may open up the case for litigation, especially in the US. That's a big market actually. A lot of psychologists work in this area where they challenge decisions made by big companies about, for example, hiring or entry criteria for universities. There were a couple of very high profile cases recently. And there might be adverse impact, which is a legal term which implies that there are group differences in testing or in test performance, which then negatively impact these groups because decisions are biased either for or more likely against them. That then impacts the hiring, probability, promotion, etc., etc. So the stuff that we're talking about is not just something that we can do and it's kind of cool and there's some kind of cool statistical models. The reason why we do this is because these decisions do have real impact in the real world, and so we need to make decisions based on our tests. We need to test all these parameters and criteria in order to have something that actually works and does not discriminate against individuals. We need to talk a little bit about terminology. I will throw around a lot of big terms in the next couple of minutes. One term that I will use is item impact. So that's essentially, it implies, is there real group difference in the probability to answer an item correctly? And that is different from differential item functioning. That is basically a statistical observation that matched test takers, so people with the same ability from different groups show a different performance on a single item. So this means that even though you might be equally intelligent, you then show a different response on a single item. And finally, we have item bias. So this is when an item becomes statistically noted for showing differential item functioning, and we can then demonstrate that this difference is actually due to something that has nothing to do with the construct or the thing that we want to measure. So basically the item is unfair. So how does it actually work? Typically you would first of all need to define what are the groups that are important for you to consider. Is it ethnicity? Is it gender? Is it social class? Is it age? Quite often we have multiple possible groups in a society that could be negatively impacted by testing, and so the first issue is we have to identify what groups are actually relevant for a specific testing purpose, or like for a specific differential item functioning identification. The second one is we need to think about how much of a bias do we actually need to see before we really scrutinize an item, right? So does it actually matter how big a bias is? We don't know yet if it's a bias, but if there's an item that seems to be performing differently, like how much should this item deviate before we kind of start looking at it? Then the next thing, and a very controversial one, when should we actually look into this? Should we always look into this, or should we look into it if there's only a negative impact on a particular group? And then we also have to think about when in the process do we need to look into these differential item functionings. For example, a test is already in use, and then we need to think about, should we revisit that test, because now there's all this evidence emerging that potentially some groups are experiencing or reporting the test differently. And definitely we should look into these issues when developing or modifying existing new tests. And finally, after we have done all our amazing statistical detective work, we have to think about, what are we going to do now? Are we going to exclude that particular item? Do we do some additional validation studies? And what should be the next steps? And what needs to happen at that moment? And typically that's something that psychologists, psychometricians, so basically statisticians and policy makers need to discuss together, which is essentially the issue of how serious would it be if we make an error when making those decisions based on a test that has some problems. And so as you can see, there are quite a few issues that need to be considered. In our sessions we are mainly focusing on the statistical aspects, but this is just to remind you that there's a larger context, and you need to think about how these tests are being used and what needs to come, or what needs to be in place before we actually start these tests, these statistical tests. So, quick recap of some classical theories. The one that you are all familiar with, even though you might not know the name, is what is called a classical test theory. And this is basically what we all do and use in psychology. It's the easiest, most widely used form of analysis. All these statistics that come out of classical test theory are readily available in all sorts of programs, in SPSS and others. They're widely used and reported. The classic example is reliability. Reliability is a classic classical test theory kind of statistical test. Classical test theory typically works at, or generally is performed at the test, so at the instrument level. We may be able to generate item statistics, but we don't really worry much about the level of any particular item. And another issue that is not so ideal about classical test theories, that the results only apply to that particular group of participants for that particular collection of items, right? So we have to remember that classical test theory, we have to always repeat our tests, and we cannot generalize beyond our specific sample at that particular moment. The way it works, it is based on a true score model. So the true score T is basically the ability or the latent variable, if you want. Then there's always some kind of error component, and that brings us or gives us an estimation of the true ability with some error. We assume that error is typically normally distributed. It is uncorrelated from the true score, so there's no connection between your ability and any kind of random variables that influence the test score, and error typically is supposed to have a mean of 0. So with that in mind, the typical test statistics that we would look at, one is item difficulty. So basically, as I said, classical test theory always works at the level of a test. So the classic statistic that you are all familiar with is reliability, so Cronbach's alpha. But we can also derive item difficulty. Typically that is related to the item mean, and discrimination. So that's also an item level statistic, and I will explain that a little bit more in just a few seconds. So that's classical test theory. There's also an alternative universe out there that is called item response theory. Item response theory is actually a whole family of all sorts of latent trait models. It looks both at the properties of items and scales, and it is often called, it's often called modern psychometrics. Modern psychometrics mainly because it is statistically and mathematically way more complex. It has many more advantages over the classical model, but it is also, much more difficult to run all these highly complex statistics. On the other hand, though, it is widely used in industry. So if you happen to get a job in some big companies, so large-scale education, assessment, testing programs, professional testing firms, they these days use some form of item response theory typically. So what are core parameters, core issues of item response theory? A core issue that I will go into a bit more detail right now is something called an item response function, or IRF. What is that? It is essentially a mathematical function that describes how an item is related to a latent variable. And so basically, what is the probability of an individual to endorse a specific item? So it links mathematically the abilities of the person taking a test, the properties of the item, and the probability of endorsing that item by that person. So it's a mathematical function. It gives us some idea about the item quality. It tells us something about the ability of the item to differentiate among respondents, because we typically want to use a test to differentiate people. Should that person go to school, or should that person wait for another year? Does this person need treatment or not? Invariance is something that can be estimated with item response functions. It relates to the position on the latent variable, and any item with a known item response function can be looked at in terms of the kind of invariance. One thing that item response theorists often claim is that these item characteristics are actually population independent within some kind of linear transformation. So once you know the item characteristics of a particular test, you should be able to apply that to new populations. So that's what IRT people typically claim. What the item response function actually, or one way of visualizing the item response function is through so-called item characteristic curves. This is basically what an ICC, an item characteristic curve, looks like, and it plots the probability of an individual to answer a question correctly, if we have, for example, an ability testing item, as a function of that person's ability. So, these are different items here. Down here we have the ability of the individual test taker, and here's the probability of a yes. Basically, the person has answered the item correctly. So as you can see, this item here, the red item, seems to be a little bit easier, because as we go up here, people with a lower level of ability have a 50% probability of answering that item correctly, whereas the blue item seems to be a little bit more difficult, but of course you need to have a higher level of ability in order to have a 50% chance to answer that item correctly. So now we can look at all sorts of different parameters within this item characteristic curve, or this item response function, and I'm going to go through some of the core parameters here in just a second. The first one is item location or difficulty. So that is basically the amount of the latent trait that a person needs in order to have a 50% chance of answering the item correctly. So the higher the location parameter, the higher the person need to be on the latent trait in order to be able to correctly answer that item. And that is pretty much similar to item difficulty in classical test theory. So what this means is similar to what I just have shown in the previous graph. Again, ability, probability of answering correctly. Here's the 50% mark, and the ability is basically the level, or the point, the location where like a person has a 50% chance to answer the item correctly. So that is the level of ability here. The second and of course we can then look at different items and look at the different item difficulties, or like item location. So we have two items here. As you can see, this item is a little bit easier because you don't need as high an ability to have a 50% chance to answer that item correctly, whereas this item is obviously a little bit more difficult. And if you remember, this is often called a uniform item bias. Why uniform? Because if you remember, the item slopes are similar. So basically the probabilities of how well the item is related to the latent trait is actually similar. Next one. Next item parameter is the discrimination, or the slope, or factor loading in classical test theory. So that's basically the steepness of the item response function at a specific item location. So it indicates how strongly related the item is to the latent variable, and that's similar to factor loadings in classical test theory. And items are typically, what we want are items that are good at discriminating, where basically we want to have some like decent slope, so that we can nicely discriminate people in terms of the latent abilities. So a small change in a latent trait lead to relatively large changes in probabilities of answering the item correctly. So that's item discrimination. the slope. So as the ability of a person increases, then we should also see an increasing ability to answer the item correctly. And obviously we would want to have an item that has relatively steep slopes here, so we can actually nicely discriminate people in terms of their ability. We don't want an item that is pretty flat in terms of their slope, because then we wouldn't be able to discriminate between individuals in terms of their underlying ability. So, and obviously we can now look at different slopes, different discrimination parameters. So this item obviously discriminates really well around this level of ability, whereas this item, like has a much shallower slope, and so therefore doesn't really discriminate that well. This is also often called non-uniform item bias. Why non-uniform? Because obviously there's these lines intersect, and there's no kind of uniform increase that is constant across different levels of ability. The last one that we need to talk about is guessing, and that is related to the intercept. The issue here, it came out of the testing literature, is there might be a guessing parameter where even people that are very, very low on a specific trait or have very low abilities may still be able to correctly guess the answer. So even people that should not get a positive score might get a score because they have a good chance of guessing the correct answer. In ability testing, this is often used with multiple choice tests, and this is basically the intercept where the function crosses the 0 point on the ability line. So it's the guessing parameter or the intercept. And so we can have also different guessing parameters, so in different groups. Again, this is an example of a uniform item bias because the slopes, the discrimination is actually the same. But obviously this item, there's a higher probability of people to get the answer correctly, even though they are very low in terms of their ability. You can of course have all sorts of differences at the same time. So here we have one where we have a different intercept, we have a different slope, and we also have a different location. So we can have all of these parameters varying at the same time. So here is an example of both of items that show both uniform and non-uniform item bias at the same time. Right? So these are the three major parameters that we need to look at within classical test theory. So why do I talk about classical test theory? Because I believe why do I talk about item response theory and classical test theory? Because people often treat them as if they are kind of somewhat independent. But the latent variable approach through models like confirmatory fact analysis can be converted into an item response theory mathematical universe, and vice versa. An item response theory approach can be converted into a latent variable approach. And that's why if you work in big testing companies, you might work with IRT approaches. There's some really, really awesome techniques out there. But at the same time, what we talk about here in this course, like all these approaches with CFA, they give you the basis to then make that transition if you need to, and vice versa. If somebody works with IRT, they can also then translate that back into, for example, a CFA framework. And if you work in these big companies these days, actually quite often people use both of these approaches at the same time. So you would use a CFA to test your dimensions, and then you would proceed and do some more sophisticated IRT model, run some more sophisticated IRT models in order to test item parameters. So long story short, both of them are mathematically comparable. And so the question now is, how do these parameters, how do these discussions link to our equivalence levels? And this is now something that you have to think about, and don't cheat. We will talk about that in just a second.